Thank you very much, Greg. I appreciate all the hard work that you folks at Ames did over the weekend. I know it must have been crazy being the first time ever doing such a meeting. So with that said, let's just dive right in. Let's go to the next slide. Or I guess I do that, right? Okay. Right now, after 4 years, we've collected over 650,000 NAC images of the surface of the moon, which is pretty much a staggering number. I can't believe it. So we've looked at about, people always ask me how much of the moon we've seen, or imaged with the NAC, and it's an easy question with a complicated answer. But right now, just 60% is not a bad number to use. With the WAC, we've mapped the whole moon something like over 40 times, and I'll show you some highlights from that. But of course, each one of those maps has unique geometry, so it is not a redundant data set. It's quite the contrary. Each mosaic is very different from the previous one, and we use that information to really learn a lot about the color of the moon and the reflectance of the moon. Let's get, on the right is a very recent result showing an albedo map for the near side of the moon. We've completed this for the whole moon, and there'll be a featured image showing off this new data set this week. Next slide. Okay, there's two slides here just highlighting the contributions at this meeting from the LROC team using LROC data, but also other data sets, Diviner, so on and so forth. I go to the next slide. I'm not going to talk about each one of these, but just point out that there's a lot of contributions from the LROC team, and I don't even know how many of the other contributions at this meeting are using LRO and LROC data. Probably, a large percentage. Okay, next slide, please. Okay, I'm going to start out talking about new results from the wide-angle camera. It's the little camera that could, like the NAC, the wide-angle camera was built by Mellon Space Science Systems in San Diego, California, which are most famous for the fantastic instruments they've built that have orbited and are still orbiting Mars. It's a very tiny camera. It fits in the palm of your hand. Next slide. It has 7 wavelengths. Next slide. And has a resolution of about 100 meters per pixel in the visible channels, about 400 meters per pixel in the UV channels. As I mentioned earlier, it's really a unique data set in terms of the repeat coverage in the fact that each one of these global mosaics is acquired with a different set of lighting, and for each pixel, different viewing geometries. We really can use those data to enable photometric studies. We now have 2 global solutions utilizing many months of data. The empirical normalization, which I just showed you an example of, I believe uses 34 months of observations, which is over 110,000 WAC images. It's a staggering amount of pixels when you start to think about it. And then we have a HAPKey solution that uses about 20 months of data. And both of these are in the process of papers being written and submitted this summer and early fall. In the future, we hope to get an extended mission, which is the second extended mission. And during that period of time, we will pitch the spacecraft forward to reduce our phase angle at very high latitudes to extend the HAPKey solution above. We're pretty good right now, about 50 degrees north and south. We'd really like to get it up to 80, 75 or 80 degrees, and that will be a major science goal of that extended mission 2 proposal. Next slide, please. Of course, as everybody probably is aware of, but I threw it in here just in case. About 2 years ago, we released a 100 meter per pixel scale global topographic map that was made from the WAC stereo observations. It's not a stereo camera per se, but there's so much overlap in the black and white mode from orbit to orbit that you can use that for parallax measurements. And our colleagues at the DLR in Germany produced this beautiful data set, and it's available, and it has been for a couple of years, on the LROC webpage. So I invite you to use that for your science studies. Next. Okay, this is a movie. Could you go and put the cursor right on and start the movie playing? Yeah. So this is the new normalized reflectance map, 643 nanometers. And it was normalized to simulate the sun 10 degrees off of nadir for everywhere on the moon. Of course, it's an impossible view. That doesn't happen in nature, but it allows us to emphasize changes in reflectance on the surface, which are predominantly controlled by the amount of iron and titanium, especially in the mare, and the age of the surface, whether it's an immature material such as the crater rays. And you see right now a beautiful view of Jackson Crater right in the center. And we come around the very bright Giordano Bruno in the upper left. We're coming back to the near side, and the albedo differences are dominated by the Mare coverage, Tycho crater, Copernicus crater, Kepler, and Aristarchus crater. Okay, I would love to let this run for about 15 minutes because it's so fantastic, but I guess we need to move on. It'll just keep going and going. Okay, next slide. Which is showing off the color. We've also, as part of the solution, done all 7 bands, not just the 643 nanometer band that you saw in the movie in the last slide. And this is a color composite using the UV in 2 visible bands at 321 nanometer, 415 nanometer, and 690 nanometer through blue, green, and red in that order. This is the central and near side, Imbrium's at the top, and Tranquillitatis is to the right. Okay, flip to the next slide, please. Okay, this is just to show, I'm going to very briefly, since I don't have a lot of time, flip through some of the products that are being produced with the WAC data set right now and are part of upcoming papers. This is part of a global titanium map made utilizing the 321 nanometer and the 450 nanometer bands. This is centered on the Tranquillitatis basin. One gratifying part of the solution was that everywhere in the highlands, the titanium abundances range from about 0 to 2 weight percent, mostly about 1 weight percent, which is right in line with the samples that we have. And the reason I mention that is because that's challenging at low values of any element to actually get a good solution. And I show Tranquillitatis here because, of course, that's an area of the moon that has the highest titanium abundances, up to about 11 or 12% in the soils, and a bit higher than that in the rocks. Okay, this is a fantastic study that I just spent the weekend reviewing a next to last draft of a manuscript that's led up by Brett Denevi, looking at UV measurements of maturation differences on the surface. And what's really fantastic about the UV is that the surface matures much faster than it does in the visible wavelength. So for old Copernican age craters, you don't really see the rays anymore. So you only see the rays in the younger Copernican age craters. And so this will be a tool for helping us separate out in time the population of Copernicans. And another fantastic result of this study is looking into the nature of swirls. Swirls are hyper immature, so to speak. They're the least mature material on the moon. And this is really good confirmation of the hypothesis from other workers that the swirls are dominantly the result of local shielding of the solar wind by these enigmatic, small localized magnetic fields on the moon. A great place to put a rover down in the future to try to understand yet another part of the enigmatic moon. Okay, next slide. Okay, this is just showing one of my favorite areas of the moon in terms of color, which is when you look at the moon from the Earth, it's in the southwest quadrant, the Mare Cognita, Mare Humorium, Mare Nubium area, where there's a lot of the historically known red spots, which, going back to the Apollo days, were thought possibly to be just prolific type volcanoes. And as you can see, there isn't a lot of color visible immediately, although the red spots do stick out in the kind of brighter tannish color in this treatment. Next slide. And here is the color ratio of the 320, or color ratio composite of the 3 ratios you see listed at the bottom. And this is where you can really bring out subtle differences in color with ratios. And this is really helping us to separate out units in the Mare and at least 2 different types of pyroclastic materials in this area of the moon. And we're in the process of interpreting these, comparing them to Earth-based spectra, Earth-based laboratory measurements. And these results will be coming out in a paper. I hope to get the manuscript submitted soon, but you know how that goes. Next slide, please. Okay, let's step back. Just one very quickly. If you look off to the right, you see La Salle Peak, which was one of these enigmatic red spots, which nobody had really known much about before Lunar Reconnaissance Orbiter. And now we have the data to really look at this feature in detail. Next slide. On the map is, on the lower left is an image map, and to the right is a sketch map of the geology made by James Ashley, who's completing a manuscript on this fascinating feature. And now we can see, by combining the binder data, the WAC color data, and the NAC high-resolution images, that this is a volcanic edifice that appears to have two more recent vents and possibly a more ancient vent. One of the problems we're working out right now is the relative timing of volcanism, the pyroclastic volcanism versus the Mare volcanism in the area. The binder data has been incredibly helpful for separating out units and showing us that indeed this is a prolific volcano. And those early guesses were right on. Next slide, please. This is to show you how the NAC data, especially looking off at angles, can really help us interpret the geology. What you see in the lower foreground are the two vents that I just spoke to. And then where it says 300-meter relief, that's sitting on top of a possible old vent that appears to be somewhat infilled by more recent eruptions. The Mare are off in the background. Okay, next slide, please. Okay, one of my favorite aspects of the narrow-angle camera data is the fact that we can take stereo by cooling off nadir from two different orbits. It's incredibly valuable measurements because from those stereo, we can make digital terrain models or topographic maps with a spatial resolution of something like 2 meters, that's our posting, to 5 meters, depending on the altitude of the spacecraft. So when we're down at 50 kilometers, we get about a 2-meter topo map. When we're up higher, say 200, we get a 5-meter topo map. These are very precise and accurate measurements, and we tie them to the LOLA data, and that really helps remove any tilts and other ambiguities that you get with stereo. So this is part of one of the many aspects of collaboration amongst the instrument teams on LROC. I wish I had more time to go into this, but we work very closely with the LOLA team, and it benefits our experiment in many, many different ways. Right now we have over 100 DTMs that are posted on our webpage for you, the science community, to pick up and start doing some fantastic work with them. And we keep adding to this collection at least every 3 months, and sometimes more frequently than that. Okay, next slide. Okay, what do you do as topography? Well, we have quite a few folks on the LRO team who are using the data for science. And this is just a quick example. I won't go into much detail because this is another presentation by Dr. Mahanti later on in the conference, where we can now, with these very high resolution DTMs, we can take very accurate measurements of very many impact craters. And rather than just using that information in a descriptive sense, we're utilizing the fact that we can take many measurements, very accurate, and using new methods, probabilistic modeling, next slide please, to use it, and it's got a funny thing when you have to flip it again for that plot to come up. Okay, to use methods to classify these in a non-priority way, and we're using this classification in this one study to determine the relative ages of large numbers of craters. And the next step would be, once we get the relative classification done, then we will use our very, very sparse handle on the ages of smaller craters on the moon from, for instance, North Ray crater. We only have a couple of measurements to try to put these into an absolute framework, but eventually we will really need to get more samples back to take these relative ages and putting them in a really meaningful absolute context. So in other words, we're developing these semi-automated methods to take advantage of these vast amounts of data, which are going to be critical for planning future missions to the moon. Next slide, please. Okay, another very gratifying part of the NAC experiment, now that we've been in orbit for 4 years, we're able to make comparisons of images that were taken early in the mission and ones that are more recent. And we have a very concerted effort going on within the LROC team to look at these images. We found, if you look very closely at the blink on the lower right, you can see a brand new, very small crater. The crater itself is not resolved, but we can see the ejecta blanket, and it's probably, the crater itself is on the order of 1 meter or 2 in diameter. We've now discovered more than 100 of these craters, and again, this is another manuscript that's in preparation, and we hope to get this result out very soon, but it's very important information for understanding the impactor rates in the Earth-Moon system and also in the inner solar system. Next slide, please. Okay, well, the LRO isn't playing a critical role while NASA is figuring out exactly what to do with their human exploration strategy and how we're going to use robots to explore the moon. And it's not only the results from LRO, but I should have also put on there Kaguya and the Chandrayaan spacecraft. And all the efforts of you sitting out in the audiences spread around the world, taking all these fantastic data sets and turning them into science results, answering some questions, but asking a lot of new questions. Next slide, please. Okay, so what's next? Now that we have all this information and these new questions, we're really looking forward to putting rovers down on the surface of the moon so that we can advance our knowledge of these questions, prove our resources, and engage the public even better than we do now in NASA exploration, and really help excite young people towards working careers in science and technology, not only in NASA. Next slide, please. Okay, we have a lot of experience with rovers, both on the moon, we being the human race, on the moon, but also on Mars, of course. There's 2 rovers running around on Mars right now. So this is not technologically challenging. It's really just a matter of getting focused on questions and a commitment to go ahead and push forward exploring the moon, which is actually pretty easy in my mind. Next slide, please. Okay, where do we go? There's many engaging targets. This is just showing one. This is part of a paper that came out recently by Spire et al. Looking at lighting resources near the pole, where you would want to go to look for water resources. Next slide, please. And another aspect of utilizing these NAC topographic models is we can use these completed DTMs for all sorts of planning future missions in terms of traverses, the easiest path to go, places you don't want to go, and also for defining the technical specifications for the rover. What kind of terrain does it need to go over to answer the specific questions? And go to the final slide, please. Okay, really, I just want to emphasize over again that this 4 years of data that all the instruments have collected are really paving the way for future exploration. That's what LRO was designed to do, and that's what it's doing beyond, well, I was going to say my expectations, but probably just about everybody's expectations. It's been an incredibly successful mission, and I think we really have about 4 or 6 more years of work to do with this beautiful spacecraft and really help bootstrap our whole strategy for human exploration and robotic exploration of the moon and beyond. So with that, I will say thank you very much.
Thanks so much, Mark. Great talk. I always go to your site and check out the latest images that have come down. It's just been fantastic. And relative to your last slide here, Mike Wargo always likes to say this, so I'll say it. Since he's not on right now, I'll say it. You know, he likes to say science enables exploration. Exploration enables science, and I think that LRO is just, and what you're doing in particular, is just such a great example of that. So we have a question from Clive. Has there been any degradation of LROC over the life of the mission? If so, what workarounds are you using?
No, absolutely not. In fact, LROC gets better and better with every image that it takes. No, there have been no degradations, and actually it does get better because now with all this data set and a lot of elbow grease applied by the folks in the SOC here, we have this fantastic calibration both in terms of geometry and radiometry and photometry, as you've seen in the last few slides about the WAC, and it's really, it enables us to eke out the last bit of useful information. So I would say that the camera just gets better and better all the time in a serious manner.
Great, great. I have a question. I know that you're aware of the Lunar Orbiter imagery reconstruction project, and I was wondering what your thoughts are, Mark, on how those newly reconstructed high-resolution images can be used with your NAC images to for discovery of craters. Would you have any recommendations on that?
Well, sure. I mean, there's all sorts of data sets out there. You know, not only the Lunar Orbiter, but the Apollo metrics and pans that are being scanned by Johnson Space Center and the Kaiguya. And all these different spacecraft give you different looks over time of the surface of the moon. So I invite folks to go and compare the most recent image data sets, the older data sets, and hunt down things that have changed on the surface. I had a very talented undergraduate spend about a month looking through Lunar Orbiter images of Copernicus and Tycho crater and comparing them to NAC images, hoping we would find a landslide or some other change in the surface that had taken place in that 40-year time span, and we didn't find any. However, now with our experiences of looking from NAC to NAC, surely if someone has the time and energy to go and co-register those data sets, and I can strongly encourage people to do that, pretty much guarantee you at some point you will find a new impact that has formed over that 40-year period.
Yeah, there's the last question here is from Wang Jun Chao, who says, how would you actually do that? How do you find the new crater? And I know Brian Day is going to be touching on that on the last talk of this session with his discussion of citizen science, but I don't know if you have any comments on that as well, Mark.
Oh, you look at a zillion pixels. Just go through and compare the images pixel by pixel. You know, it's not hard. It's just, you know, a lot of elbow grease. Yeah.
Okay. All right. Well, thanks again for a great talk. Really enjoyed it, and congratulations on such a successful instrument. It's hard to believe it's been going for 4 years now, and I look forward to a whole lot more data in the coming years as well. So our next